Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on applications of Pythagoras. So in previous lessons, you learned how to find the length of an unknown side, whether that be a shorter side or the longest side of a right-angled triangle. And now we're going to use this to solve problems like the one that's on the screen. So the question we start with, a person walks 6 kilometers due south, 8 kilometers due east. How far are they from their starting point? So whenever you're given a worded question like this and not given a diagram, always draw your own diagram. Now, because we're doing Pythagoras, there should be a right-angled triangle somewhere in your diagram. So let's say the person starts here. So they go 6 kilometers due south, and then 8 kilometers due east. So draw a compass if you're not sure. Remember, it goes north, east, south, west. So they would then go 8 kilometers due east. Now, north and east, north and west, south and east, south and west are always at right angles. That would be a right angle there. We don't actually have a triangle, so what we can do is join it up to make a triangle. We're interested in this length here because the person started here, went south, and then east, and ended up here. And I want to know that red distance, how far they are from their starting point. So the hard part of this question is actually done. Now that we've got the diagram, we just need to find the length of a side as we've done a million times in previous exercises. So x is the hypotenuse, the longest side, because it is facing the right angle. So remember, when you're finding the hypotenuse, it's the square root of a squared plus b squared. There's a plus under the square root when you're finding the longest side. And if you put that in your calculator, you just get 10. So here it would be kilometers because the other two sides were in kilometers. So how far are they from their starting point? 10 kilometers. They would need to walk 10 kilometers in this northwest direction to be back where they started. How easy is that? Let's look at another example. So let's do this question here. A ladder, 12 meters in length, leans against a wall, reaches 9 meters up the wall, and we're going to calculate the distance from the base of the ladder to the base of the wall. Once again, not given a diagram, let's draw one. So this will be our ladder leaning against a wall. So that dotted line is the wall. Okay, we can put labels if we want. So ladder up against the wall. So we were told that the ladder is 12 meters in length. So that there is 12. So if it reaches 9 meters up the wall, this length here is 9 meters. Now, once again, as I said in the previous example, somewhere we should have a right-angled triangle. So let's turn this into a triangle. It'll be right-angled because the wall will be 90 degrees to the floor. So we're asked how far is the base of the ladder. So the base of the ladder is here. The base of the wall is here. So we're looking for this distance here. And I'll call that y. So again, we have done the hard part of this question. So what we do now is just calculate a distance using Pythagoras that we've done a million times before. So this time we're finding a shorter side. So y will be the square root of c squared, hypotenuse squared, minus the shorter side. So you minus when you're finding one of the shorter sides. So this will be the square root of 144 minus 81, which is the square root of 63. So the square root of 63, that's exact form. We can put it in our calculator and round it to 2 decimal places. It will be about 7.94 meters. So how far is the base of the ladder from the base of the wall? The base of the ladder is about 7.94 meters from the base of the wall. All right, let's look at an example now that's slightly harder. So now we're going to use Pythagoras to find the area of a triangle with side length 8 centimeters. So you're probably thinking, hang on a minute, Pythagoras has nothing to do with area. Well, let's once again start by drawing a diagram since we're not given one. So we have a triangle and it's equilateral. Sorry about my bad drawing. Each side 8 centimeters, right? So if I want to find the area of this triangle or any other triangle, remember I need the base times the perpendicular height. So that's 90 degrees. So yes, Pythagoras isn't really about area, but what I'm going to use Pythagoras for in this question is to find this perpendicular height here. Because once I know that, the area of the triangle is just base times perpendicular height divided by 2. Now, if the triangle is isosceles or equilateral, you can use this trick. It will actually divide the base in half. So this length here in blue will be half of 8, which is 4, and then this length here will also be 4. So what you've actually got here is a right-angled triangle. This is the perpendicular height we want to find. Here, this is the hypotenuse of 8 centimeters, and the shorter side is 4 centimeters. So this triangle here, I've just drawn it down here. Okay, so to find h in this triangle is really easy. It's like all the others that we've done a million times before. So h, the height, is a shorter side, so it'll be the square root of longer side minus the other shorter side, 8 squared minus 4 squared. So if you put that in your calculator, you get square root of 48, that is about 6.93. So I've rounded it to 2 decimal places again, and it'll be centimeters. So I've used Pythagoras to find the perpendicular height. I can't find the area of this triangle, or at least we don't know yet how to find the area of this triangle without knowing the perpendicular height. So now that we've found it, the area of the triangle, I just use this formula here. The area is the base. So this is the base of the whole triangle now. So it's 8 times perpendicular height divided by 2. So remember to divide by 2. People always forget that when they're finding the area of a triangle. So if I put that on my calculator, I get about 27.2 centimeters squared. This time I've just rounded to 1 decimal place, okay? So the rounding doesn't matter too much here. All right, just one more example I need to go through. So we know that if we have a right-angled triangle, then a squared plus b squared equals c squared. That is Pythagoras' theorem that we've been using a million times. And of course, remember, c is always the longest side. But it turns out the converse, the other form of that statement, is true. If you have a triangle where a squared plus b squared equals c squared, then the triangle is right-angled. And you'll usually be able to tell which is the right angle, okay? So let's say I have a triangle like this. I'm going to give it measurements 7, 9, and 11. So I want to check, is this triangle right-angled? Now, we don't want to just say, oh yeah, this angle here looks like it's about 90 degrees, okay? We want to be definitive. So let's rub that out. What we're going to do is check whether Pythagoras' theorem holds. So this value c, it doesn't matter really which of the shorter sides you call a and which you call b. So now I'm going to check, does a squared plus b squared equal c squared? So we have a squared plus b squared. So if you put that on your calculator, you get 81 plus 49, which is 130. But c squared is 11 squared, 121. So in this example, a squared plus b squared doesn't equal c squared. So Pythagoras' theorem doesn't hold, therefore this triangle is not right-angled. Okay, so that's another application of Pythagoras. We can check whether or not a given triangle is right-angled. Alright, please let me know if you have any questions. Sorry for the long video. This has been the luckiest maths teacher in the world. Have a great day.